Revolutionary quantum state unveiled. Radiation-proof self-charging computers ahead? Imagine a future where computers not only charge themselves but also operate flawlessly in the harshest environments, like deep space, shielded from destructive radiation. Sounds like science fiction, right? But here's the twist. Scientists have just uncovered a groundbreaking phenomenon that could make this vision a reality. This discovery centers around a completely new quantum state of matter, one that could redefine how we think about technology and its limits. At the heart of this revelation is something called the Spin-Triplet Excitonic Insulator. To fully grasp what this means, let's break it down into simpler terms. Modern electronics rely on semiconductors, materials that control the flow of electrons, tiny negatively charged particles that power everything from your smartphone to satellites. These semiconductors also feature something called electron holes, which are essentially gaps where an electron should be, but isn't. Under specific conditions, these electrons and holes can pair up to form a unique entity known as an exciton. Think of it like a dance partnership between two particles, but one that's fragile and doesn't last long under normal circumstances. Now, here's where things get even more fascinating. In rare cases, these excitons can stabilize and spread across a material, creating what's known as an excitonic insulator. Until now, researchers had only observed one type of excitonic insulator, referred to as a spin singlet. In this state, the electron and hole behave almost like opposites. Their intrinsic angular momentum, or spin, is aligned in opposite directions. It's akin to two dancers spinning in perfect opposition to each other. However, the newly discovered state flips this dynamic entirely. In the spin-triplet state, both the electron and the hole spin in the same direction, a configuration so unusual that it has eluded detection until now. Think of it like discovering a new phase of water, something beyond liquid ice or vapor, explained Professor Luis Jauregui, the lead researcher behind the study at the University of California, Irvine. It's a completely novel phase of matter. If we could somehow hold it in our hands, it would emit a brilliant light with incredibly high frequency. The discovery was made using a specialized material composed of hafnium and tellurium, which was subjected to extraordinarily strong magnetic fields reaching up to 70 Tesla. For context, your average refrigerator magnet generates a field of just 0.1 Tesla, meaning the experimental setup involved magnetic forces thousands of times stronger than anything you'd encounter in daily life. Under such intense conditions, the material underwent a dramatic transformation. Instead of conducting electricity as it normally would, it entered this exotic new state where its properties shifted entirely. What does this mean for practical applications? Well, this discovery opens the door to technologies that rely on manipulating particle spins rather than merely moving electrical charges around. Known as spintronics, this emerging field aims to create ultra-efficient devices capable of performing complex tasks while consuming far less energy than traditional electronics. And this is the part most people miss. The implications go far beyond faster or more efficient gadgets. Spin-based systems could revolutionize industries like space exploration, where equipment must endure extreme levels of cosmic radiation. Traditional computers struggle in such environments because radiation disrupts the delicate balance of electronic circuits. But imagine sending spacecraft equipped with self-charging, radiation-resistant computers into the farthest reaches of the galaxy. Suddenly, humanity's ability to explore the cosmos becomes exponentially greater. Of course, there are still many unanswered questions. While the potential seems limitless, translating this discovery into real-world technology will require overcoming significant challenges. Can we replicate these conditions outside of a lab setting? How scalable is this approach? And perhaps most intriguingly, what other undiscovered states of matter might be lurking just out of sight? But here's where it gets controversial. Some experts argue that focusing heavily on quantum states like this might divert resources away from solving pressing issues closer to home, such as improving access to clean energy or addressing climate change. Others counter that breakthroughs in fundamental science often lead to unexpected innovations with widespread benefits. So where do you stand? Do you think humanity should prioritize exploring the mysteries of quantum mechanics over tackling immediate global concerns? Let us know in the comments below. We'd love to hear your thoughts. UC Irvine scientists discover new state of quantum matter for better computing in deep space. UC Irvine scientists have made a groundbreaking discovery that could revolutionize computing in deep space. They've observed a new state of quantum matter that could lead to the development of self-charging, radiation-resistant computers. This new phase of matter, similar to how water can exist as liquid, ice, or vapor, has only been theoretically predicted until now. It's a quantum liquid composed of electrons and their counterparts, known as holes, spontaneously pairing and forming exotic states called excitons. The electrons and holes spin together in the same direction, creating a bright, high-frequency glow. The key to creating this new quantum matter was applying a high-intensity magnetic field of up to 70 teslas to a material called hafnium pentatelluride. As the magnetic field was applied, the material's ability to carry electricity suddenly dropped, indicating its transformation into this exotic state. This discovery could allow signals to be carried by spin rather than electrical charge, offering a new path toward energy-efficient technologies, like spin-based electronics or quantum devices. Unlike conventional materials used in electronics, this new quantum matter isn't affected by radiation, making it ideal for space travel. Companies like SpaceX, planning human-piloted space flights to Mars, could benefit from computers that can withstand prolonged exposure to radiation. This new quantum matter could make that possible. The possibilities that could open up as a result of this discovery are yet to be seen. But it's clear that this new state of quantum matter has the potential to revolutionize computing in deep space and beyond. Newly discovered material could power self-charging computers for interplanetary travel. Imagine a breakthrough so powerful it could revolutionize the future of computing and space travel. Self-charging computers that thrive in the harshest environments of deep space. This is no longer science fiction. Scientists at the University of California, Irvine, UCI, have uncovered a previously unknown state of matter within a newly engineered material, a discovery that could dramatically enhance quantum computing and enable the development of ultra-efficient, radiation-proof computers designed for interplanetary missions. Published in the prestigious journal Physical Review Letters, this research reveals a never-before-seen quantum phase where electrons and their positively charged counterparts, called holes, spontaneously pair up to form unusual entities known as excitons. But here's where it gets truly fascinating. Unlike typical excitons, these particles spin in the same direction, creating a novel and exotic quantum structure. Professor Louis A. Jauregui, the study's lead author and a physicist at UCI, likens this new state to discovering a fourth phase of water, beyond liquid, ice, and vapor. If we could hold this material in our hands, he explains, it would glow with a bright, high-frequency light, signaling its unique quantum nature. The star of this discovery is a compound called hafnium pentatelluride, synthesized by Jinyu Liu, a postdoctoral researcher in Jauregui's lab and the paper's first author. To verify this extraordinary quantum state, the team exposed the material to extremely strong magnetic fields, up to 70 teslas, which is about 700 times stronger than the magnetic field of a typical refrigerator magnet, at Los Alamos National Laboratory, LANL, in New Mexico. What caught the researchers by surprise was the material's sudden loss of electrical conductivity when subjected to these intense magnetic fields. This abrupt change signaled the transition into the new quantum phase. Jauregui points out that this suggests a radical shift in how information could be transmitted in future devices, not through the flow of electric charge as in today's electronics, but via the spin of particles. This spin-based communication could drastically cut energy use and pave the way for spintronics, a cutting-edge field aiming to create more stable and energy-efficient quantum devices. But the potential impact doesn't stop at energy savings. Unlike traditional semiconductors, hafnium pentatelluride is remarkably resistant to radiation. a crucial advantage for electronics destined for long-term space missions. If we want computers that can survive on Mars, or during interstellar voyages, Hareggi stresses, we need materials that won't degrade after years of exposure to cosmic rays. This resilience could be a game-changer for companies like SpaceX, which are actively planning human missions to the Red Planet. However, Hareggi cautions that it's still early days, and the full range of applications remains to be seen. This breakthrough was the result of a collaborative, multidisciplinary effort. Alongside Liu, graduate students Robert Welser and Timothy McSorley, and university researcher Triet Ho from UCI contributed to the project. The theoretical framework was developed by a team at LANL, including Shizang Lin, Varsha Subramanian, and Avad Saxena, who helped interpret the experimental data. The challenging high magnetic field experiments were supported by experts Laurel Winter, Michael T. Petties from LANL, and David Graff from the National High Magnetic Field Laboratory in Florida. While commercial use of hafnium pentatelluride is still a distant goal, this discovery marks a significant milestone in the field of materials physics. We don't yet know all the doors this will open, Hareggi admits, but venturing into this new quantum territory is incredibly exciting. As the space industry and quantum computing communities watch closely, hafnium pentatelluride stands out as a promising candidate to tackle two of the most pressing technological challenges of our time: dramatically improving energy efficiency and ensuring electronic devices can endure the unforgiving conditions of space. But here's the part most people miss. Could this discovery also spark debates about the future direction of quantum technology? Will spin-based electronics truly replace charge-based systems, or are there hidden limitations yet to be uncovered? What do you think? Are we on the brink of a quantum revolution, or is this just another step in a long journey? Share your thoughts and join the conversation. For more fascinating insights and updates, subscribe to LBV Magazine's English edition and stay informed about the latest breakthroughs shaping our world and beyond.